Blackwell is not a chip. Blackwell is the name of a platform. People think we make GPUs, and we do, but GPUs don't look the way they used to. Here's the if you will, the heart of the Blackwell system. And this inside the company is not called Blackwell, it's just a number. And this is Blackwell sitting next to, this is the most advanced GPU in the world in production today. This is Hopper. This is Hopper. Hopper changed the world. This is Blackwell. It's okay, Hopper. You're very good. Good boy. Oh, good girl. 208 billion transistors, and so you could see, I can see, there's a small line between two dies. This is the first time two dies have abutted like this together in such a way that the two dies think it's one chip. There's 10 terabytes of data between it, 10 terabytes per second, so that these two sides of the Blackwell chip have no clue which side they're on. There's no memory locality issues, no cache issues. It's just one giant chip. And so when we were told that Blackwell's ambitions were beyond the limits of physics, the engineer said, so what? And so this is what happened. And so this is the Blackwell. The first one is form-fit-function compatible to Hopper. And so you slide on Hopper and you push in Blackwell. That's the reason why one of the challenges of ramping is going to be so efficient. There are installations of Hoppers all over the world, and they could be the same infrastructure, same design, the power, the electricity, the thermals, the software, identical, push it right back. And so this is a Hopper version for the current HGX configuration. And this is what the second Hopper looks like this. Now this is a prototype board. Take this, it has two Blackwell chips and 4 Blackwell dies connected to a Grace CPU. The Grace CPU has a super fast chip-to-chip link. What's amazing is this computer is the first of its kind where this much computation, first of all, fits into this small of a place. Second, it's memory coherent. They feel like they're just one big happy family working on one application together. And so everything is coherent within it. Just the amount of, you saw the numbers. There's a lot of terabytes this and terabytes that. But this is a miracle. This is what are some of the things on here? There's NVLink on top, PCI Express on the bottom. On your, which one is mine and your left? One of them, it doesn't matter. One of them is a CPU chip-to-chip link. It's my left or your, depending on which side. I was trying to sort that out, and I just kind of, doesn't matter. Hopefully it comes plugged in, so. Okay, so this is the Grace Blackwell system. But there's more. So it turns out, all of the specs is fantastic, but we need a whole lot of new features in order to push the limits beyond, if you will, the limits of physics. We would like to always get a lot more X factors. And so one of the things that we did was we invented another transformer engine, the second generation. It has the ability to dynamically. And so this new transformer engine, we have a 5th generation NVLink. It's now twice as fast as Hopper, but very importantly, it has computation in the network. And the reason for that is because when you have so many different GPUs working together, we have to share our information with each other. We have to synchronize and update each other. And every so often, we have to reduce the partial products and then rebroadcast out the partial products, the sum of the partial products, back to everybody else. And so there's a lot of what is called all reduce and all to all and all gather. It's all part of this area of synchronization and collectives so that we can have GPUs working with each other. Having extraordinarily fast links and being able to do mathematics right in the network allows us to essentially amplify even further. So even though it's 1.8 terabytes per second, it's effectively higher than that. And so it's many times that of Hopper, all encrypted. And so we now have the ability to encrypt in transmission, and when we're computing it, it is in a trusted environment, trusted engine environment. And the last thing is decompression. Moving data in and out of these nodes when the compute is so fast becomes really essential. And so we've put in a high line speed compression engine and it effectively moves data 20 times faster in and out of these computers. These computers are so powerful and there's such a large investment, the last thing we want to do is have them be idle. And so all of these capabilities are intended to keep Blackwell fed and as busy as possible. Overall, compared to Hopper, it is 2.5 times the FP8 performance for training. Even though the computation speed is the same, the bandwidth that's amplified because of the memory, the amount of parameters you can store in the memory is now amplified. FP4 effectively doubles the throughput. This is vitally important for inference. One of the things that is becoming very clear is that whenever you use a computer with AI on the other side, when you're chatting with the chatbot, when you're asking it to review or make an image, remember, in the back is a GPU generating tokens. Some people call it inference. We've increased computation by 1,000 times, 8 years, 1,000 times. Remember, back in the good old days of Moore's Law, it was 2x, well, 5x every, 10x every 5 years. That's easiest math. 10x every 5 years, 100 times every 10 years. 100 times every 10 years in the middle, in the heydays of the PC revolution. 100 times every 10 years. In the last 8 years, we've gone 1,000 times. We have 2 more years to go. And so that puts it in perspective. The rate at which we're advancing computing is insane, and it's still not fast enough, so we built another chip. It's just an incredible chip. We call it the NVLink switch. It's 50 billion transistors. It's almost the size of Hopper all by itself. This switch chip has 4 NVLinks in it, each 1.8 terabytes per second, and it has computation in it, as I mentioned. What is this chip for? If we were to build such a chip, we can have every single GPU talk to every other GPU at full speed at the same time. That's insane. It doesn't even make sense. But if you could do that, if you can find a way to do that and build a system to do that, that's cost effective. That's cost effective. How incredible would it be that we could have all these GPUs connect over a coherent. Well, one of the great inventions in order to make it cost effective is that this chip has to drive copper directly. The SerDes of this chip is just a phenomenal invention so that we could do direct drive to copper. And as a result, you can build a system that looks like this. Now this system is kind of insane. This is 1 DGX. This is 720 petaflops, almost an exaflop for training, and the world's first 1 exaflops machine in 1 rack. Just so you know, there are only a couple, 2, 3 exaflops machines on the planet as we speak. And so this is an exaflops AI system in 1 single rack. Well, let's take a look at the back of it. So this is what makes it possible. That's the back, the DGX NVLink spine. 130 terabytes per second goes through the back of that chassis. That is more than the aggregate bandwidth of the internet. So we could basically send everything to everybody within a second. For large language models like ChatGPT and others like it, the blue line is Hopper. I gave you, imagine we didn't change the architecture of Hopper, and we just made it a bigger chip. We just used the latest, greatest 10 terabytes per second. We connected the 2 chips together. We got this giant 208 billion parameter chip. How would we have performed if nothing else changed? And it turns out quite wonderfully, and that's the purple line, but not as great as it could be. And that's where the FP4 Tensor Core, the new transformer engine, and very importantly, the NVLink switch. And it is packaged and optimized to run across NVIDIA's installed base, which is very, very large. What's inside it is incredible. You have all these pre-trained, state-of-the-art open source models. They could be open source, they could be from one of our partners, it could be created by us, like NVIDIA Moment. It is packaged up with all of its dependencies. So CUDA, the right version, cuDNN, the right version, TensorRT, LLM, distributing across the multiple GPUs, Triton Inference Server, all completely packaged together. It's optimized, depending on whether you have a single GPU, multi-GPU, or multi-node of GPUs, it's optimized for that. And it's connected up with APIs that are simple to use. Now think about what an AI API is. An AI API is an interface that you just talk to. And so this is a piece of software in the future that has a really simple API, and that API is called Human. And these packages, incredible bodies of software, will be optimized and packaged, and we'll put it on a website. And you can download it, you could take it with you, you could run it in any cloud, you could run it in your own data center, you can run in workstations if it fit. And all you have to do is come to ai.nvidia.com. We call it NVIDIA Inference Microservice, but inside the company, we all call it NIMS. Okay? Maybe it's an optimization software, a combinatorial optimization algorithm. Maybe it's some basic calculator. Maybe it's pandas to do some numerical analysis on it. And then it comes back with its answer, and it gets combined with everybody else's, and because it's been presented with this is what the right answer should look like, it knows what right answers to produce, and it presents it to you. We can get a report every single day at top of the hour that has something to do with a build plan or some forecast or some customer alert or some bugs database or whatever it happens to be, and we could assemble it using all these NIMs. And because these NIMs have been packaged up and ready to work on your systems, so long as you have NVIDIA GPUs in your data center or in the cloud, this NIMs will work together as a team and do amazing things. And so we decided, this is such a great idea, we're going to go do that. There's so many companies that would like to build, they're sitting on gold mines. The enterprise IT industry is sitting on a gold mine. It's a gold mine because they have so much understanding of the way work is done. They have all these amazing tools that have been created over the years, and they're sitting on a lot of data. If they could take that gold mine and turn them into co-pilots, these co-pilots could help us do things. And so just about every IT franchise, IT platform in the world that has valuable tools that people use is sitting on a gold mine for co-pilots. And they would like to build their own co-pilots and their own chatbots. And so we're announcing that NVIDIA AI Foundry is working with some of the world's great companies. SAP generates 87% of the world's global commerce. Basically, the world runs on SAP. We run on SAP. NVIDIA and SAP are building SAP Joule co-pilots using NVIDIA NeMo and DGX Cloud. ServiceNow, they run 85% of the world's Fortune 500 companies run their people and customer service operations on ServiceNow. And they're using NVIDIA AI Foundry to build ServiceNow Assist virtual assistants. Cohesity backs up the world's data. They're sitting on a gold mine of data. Hundreds of exabytes of data, over 10,000 companies. NVIDIA AI Foundry is working with them, helping them build their Gaia generative AI agent. Snowflake is a company that stores the world's digital warehouse in the cloud and serves over 3 billion queries a day for 10,000 enterprise customers. Snowflake is working with NVIDIA AI Foundry to build copilots with NVIDIA NeMo and NIMS. NetApp, nearly half of the files in the world are stored on-prem on NetApp. NVIDIA AI Foundry is helping them build chatbots and copilots like those vector databases and retrievers with NVIDIA NeMo and NIMS. And we have a great partnership with Dell. Everybody who is building these chatbots and generative AI, when you're ready to run it, you're going to need an AI factory. And nobody is better at building end-to-end systems of very large scale for the enterprise than Dell. And so anybody, any company, every company will need to build AI factories. And it turns out that Michael is here. He's happy to take your order. Ladies and gentlemen, Michael Dell. Computer. It's that AI computer that now it's going to be watching video, and maybe it's doing synthetic data generation, and maybe there's a lot of human examples. Just as we have human examples in text form, we're going to have human examples in articulation form. And the AIs will watch us, understand what is happening, and try to adapt it for themselves into the context. And because it can generalize with these foundation models, maybe these robots can also perform in the physical world fairly generally. So I just described, in very simple terms, essentially what just happened in large language models, except the ChatGPT moment for robotics may be right around the corner. And so we've been building the end-to-end systems for robotics for some time. I'm super, super proud of the work. We have the AI system, DGX. We have the lower system, which is called AGX, for autonomous systems, the world's first robotics processor. When we first built this thing, people are, what are you guys building? It's an SoC. It's one chip. It's designed to be very low power, but it's designed for high-speed sensor processing and AI. And so if you want to run transformers in a car, or you want to run transformers in anything that moves, we have the perfect computer for you. It's called the Jetson. And so the DGX on top for training the AI, the Jetson is the autonomous processor, and in the middle, we need another computer. Whereas large language models have the benefit of you providing your examples and then doing reinforcement learning human feedback. What is the reinforcement learning human feedback of a robot? Well, it's reinforcement learning physical feedback. That's how you align the robot. That's how the robot knows that as it's learning these articulation capabilities and manipulation capabilities, it's going to adapt properly into the laws of physics. And so we need a simulation engine that represents the world digitally for the robot, so that the robot has a gym to go learn how to be a robot. We call that virtual world Omniverse. And the computer that runs Omniverse is called OVX. And OVX, the computer itself, is hosted in the Azure cloud. Okay? And so basically we built these three things, these three systems. On top of it, we have algorithms for every single one. Now, I'm going to show you one super example of how AI and Omniverse are going to work together. The example I'm going to show you is kind of insane, but it's going to be very, very close to tomorrow. It's a robotics building. This robotics building is called a warehouse. Inside the robotics building are going to be some autonomous systems, digital twin capability. We also have turned Omniverse into an AI and integrated it with the ability to chat USD. The language of our language is, human, and Omniverse's language, as it turns out, is universal scene description. And so that language is rather complex, and so we've taught our Omniverse that language. And so you can speak to it in English, and it would directly generate USD. And it would talk back in USD, but converse back to you in English. You could also look for information in this world semantically. Omniverse, let's take a look.
Siemens technologies transform the everyday for everyone. Teamcenter X, our leading product lifecycle management software from the Siemens Accelerator platform, is used every day by our customers to develop and deliver products at scale. Now we are bringing the real and the digital worlds even closer by integrating NVIDIA AI and Omniverse technologies into Teamcenter X. Omniverse APIs enable data interoperability and physics-based rendering to industrial-scale design and manufacturing projects. Our customers, HD&A, market leader in sustainable chip manufacturing, builds ammonia and hydrogen-powered chips, often comprising over 7 million discrete parts. With Omniverse APIs, Teamcenter X lets companies like HD&A unify and visualize these massive engineering data sets interactively and integrate generative AI to generate 3D objects or HDRI backgrounds to see their projects in context. The result, an ultra-intuitive photoreal, physics-based digital twin that eliminates waste and errors, delivering huge savings in cost and time. And we are building this for collaboration, whether across more Siemens accelerator tools like Siemens NX or Star CCM+, or across teams working on their favorite devices in the same scene together. And this is just the beginning. Working with NVIDIA, we will bring accelerated computing, generative AI, and Omniverse integration across the Siemens accelerator portfolio.
We also today are announcing this incredibly advanced new SDK. We call it Isaac Perceptor. Isaac Perceptor, most of the robots today are pre-programmed. They're either following rails on the ground, digital rails, or they'd be following April tags. But in the future, they're going to have perception. And the reason why you want that is so that you could easily program it. You say, would you like to go from point A to point B? And it will figure out a way to navigate its way there. So by only programming waypoints, the entire route could be adaptive. The entire environment could be reprogrammed, just as I showed you at the very beginning with the warehouse. You can't do that with pre-programmed AGVs. If those boxes fall down, they just all gum up and they just wait there for somebody to come clear it. And so now, with the Isaac Perceptor, we have incredible state-of-the-art vision odometry, 3D reconstruction, and in addition to 3D reconstruction, depth perception. The reason for that is so that you can have two modalities to keep an eye on what's happening in the world. Isaac Perceptor. The most used robot today is the manipulator, manufacturing arms, and they are also pre-programmed. The computer vision algorithms, the AI algorithms, the control and path planning algorithms that are geometry aware, incredibly computationally intensive. We have made these CUDA accelerated. So we have the world's first CUDA accelerated motion planner that is geometry aware. You put something in front of it, it comes up with a new plan and articulates around it. It has excellent perception for pose estimation of a 3D object. Not its pose in 2D, but its pose in 3D. So it has to imagine what's around and how best to grab it. So the foundation pose, the grip foundation, and the articulation algorithms are now available. We call it Isaac Manipulator. And they also just run on NVIDIA's computers. We are starting to do some really great work in the next generation of robotics. The next generation of robotics will likely be a humanoid robotics. We now have the necessary technology, and as I was describing earlier, the necessary technology to imagine generalized human robotics. In a way, human robotics is likely easier, and the reason for that is because we have a lot more imitation training data that we can provide the robots because we are constructed in a very similar way. it is very likely that the humanoid robotics will be much more useful in our world because we created the world to be something that we can interoperate in and work well in. And the way that we set up our workstations and manufacturing and logistics, they were designed for humans. They were designed for people. And so these humanoid robotics will likely be much more productive to deploy. While we're creating, just like we're doing with the others, the entire stack. Starting from the top, a foundation model that learns from watching video, human examples. It could be in video form, it could be in virtual reality form. We then created a gym for it called Isaac Reinforcement Learning Gym, which allows the humanoid robot to learn how to adapt to the physical world. And then an incredible computer, the same computer that's going to go into a robotic car, this computer will run inside a humanoid robot called Thor. It's designed for transformer engines. We've combined several of these into one video. This is something that you're going to really love. Take